Welcome back. I have a post here with a flag. It is supported by two cables in which you have tension forces. You have all the dimensions and four magnitudes in the image. The center of the origin of the coordinate frame, that's O. And now I have a question for you. What is the resultant moment due to these two forces about point O? So we want to find MR about point O due to these two forces. As you can see, now we are dealing with a three-dimensional problem. That means that we have to learn how to calculate moments in 3D. Now, earlier we learned about the dot product. You had two vectors, A and B, and an angle theta between them. The dot product was defined like this: vector A dot vector B, and that would be the magnitude of A times the magnitude of B times cosine theta. The final result gave you a scalar. And if you remember, then the dot product gave you the component of one vector parallel to another vector. And only that component was multiplied by that other vector. So for example, here, I only multiply this B parallel by this A vector. So you had A times B parallel, then B parallel was B times cosine theta. And so you would end up with A times B times cosine theta. However, there is another kind of product that vectors can have. Imagine again that we have two vectors, A and B, and the angle theta between them, just like before. And now, what if I want to do the opposite? I want to take the component of B that is perpendicular to A, so you have 90 degrees here, and then I multiply this B perpendicular by A. So something like this. How would you do it? Well, you can get B perpendicular like this. B perpendicular equals B times sine theta. And so that means that this one here, it would be B times sine theta times A, or A times B times sine theta. Just as a side note, remember that when you calculate moments, then the force and the moment arm must be perpendicular to each other. So you needed to have something like this. This is your moment arm, this is your force, and you have 90 degrees here. And here we are decomposing this B vector into two components. One is parallel to A, and the other one is perpendicular to A. And then we are taking the component perpendicular to A, and we are multiplying it by A. So you can already imagine that what we are doing here can be something useful for moment calculations. Similarly, if I want to multiply A perpendicular by B, then A perpendicular equals A times sine theta, so A perpendicular times B. Again, it would be A times B times sine theta, the same thing. Only in this case, I take the A vector and I decompose it in such a way that I have one component parallel to B and the other one perpendicular to B. But either way, you get the same scalar, no matter whether you multiply B perpendicular by A or A perpendicular by B. You will get the same scalar. However, notice one thing. When I have B perpendicular times A, then I cause counterclockwise rotation. And when I have A perpendicular times B, then I cause clockwise rotation. And you already know that the direction of a rotation vector is perpendicular to the rotation plane according to the right-hand rule. So when you have a counterclockwise rotation, then the rotation vector points out of the screen towards you. And the clockwise rotation gives you a rotation vector into the screen away from you. In both cases, the rotation vector is perpendicular to both A and B. When you had a dot product, A dot B, then it did not matter whether you had A parallel times B or A times B parallel. So we could leave it as a scalar. However, now it matters whether you have B perpendicular times A or A perpendicular times B. You would get either counterclockwise or clockwise rotation. It means that now we get a result that is a vector, not a scalar. In both cases, we have a rotation vector that is perpendicular to vectors A and B. But B perpendicular times A gives you counterclockwise rotation, and A perpendicular to B gives you clockwise rotation. And therefore, we have to add a unit vector to this definition here. So we will have A times B times sine theta times a unit vector sub c. This unit vector sub c is a unit vector that equals +1 for counterclockwise rotation, and it's -1 for clockwise rotation. And this definition is what we call the cross product. Just like for the dot product, we had this definition. For the cross product, we have A cross B, and that equals A magnitude times B magnitude times sine theta times this unit vector sub c. That's the cross product definition, and it follows the right-hand rule. Again, these are your two vectors, A and B. Since you have to rotate counterclockwise when you go from A to B, your u sub c will be +1, and it will be perpendicular to both A and B, so it will be this one here, and it's perpendicular to A and B, so your right hand is first like this, where its fingers are in the direction of vector A, and then you curl these fingers towards B. These are your knuckles here, so your fingers go from this position to this position, and your right hand thumb points in this direction. And so it is important to note that this u sub c, whether it's +1 or -1, it's perpendicular to both A and B. That's important to remember. And therefore, this vector here that has the same direction like u sub c, that's A cross B, which is A times B times sine theta times u sub c. And remember, in this case, this magnitude is B perpendicular times A. It's this case here, not this one, but this one. And also, what is important to understand is that this one here, that's the magnitude of the cross product. That's essentially the length of this red arrow. And then this blue arrow, well, that's just +1. So you multiply the magnitude by +1. The point of this unit vector is to show you the direction and not to scale the cross product. However, if instead of A cross B, I have B cross A, then the rotation from B to A is clockwise. So here, when I moved from A to B, I had A cross B. Then now, when I move from B to A, I have B cross A. Now I have clockwise rotation. Now I have this case here, which means that U sub C equals -1 and is perpendicular to both A and B. It means that now U sub C points down, but as you can see, it's still perpendicular to A and B, and that means that B cross A also points down in the same direction. Even though the direction is different from the first version, the magnitude, it's still the same. The length of the red vector is still the same. It's just in the opposite direction. And again, just like in the first case, this red vector is also perpendicular to both A and B. And in order not to get confused with all this, my recommendation is always use the right-hand rule. If you have A cross B, then you just take your right hand, you first have A, so your right hand fingers at the beginning point in the direction of A, and then you curl your fingers towards B. In this case, however, you have B cross A, so you take your right hand, your fingers first point in the B direction, and then you curl your right hand fingers in the direction of A. And so your right hand thumb will point down. So that's the cross product. And of course, when you have this case, B cross A, then that's this scenario here. The magnitude here, that's A perpendicular B. It gives you clockwise rotation. Welcome back. Now that we have our definition for the cross product, how would we use it to calculate a moment? Imagine that we have our XYZ coordinate frame. You have a random position vector from the origin O, and then I apply a random force vector to the tip of the position vector. Imagine that these two vectors, R and F, lie on a plane, this blue plane here. Then a moment vector about point O is created, and this moment vector is perpendicular to this blue plane, and well, according to the right-hand rule, this would be the sense of rotation of this moment vector. Let's look at this plane from the top. So this is my R vector, this is the F vector, this is point O, and so what I can do now, I can take this force vector and I can shift it. I will put its tail where this point O is, and so they have an angle theta here. And now, just like I had with A cross B here, which was B perpendicular times A times the unit vector in the counterclockwise direction, because you had counterclockwise rotation here, and so you could rewrite this entire thing like this: A times B times sine theta times the unit vector. In the same way, I can have here F perpendicular, which is perpendicular to this vector R, the position vector, and so in here I would have R cross F, which would be F perpendicular times the position vector times the unit vector, which would give you counterclockwise rotation. And so that means that you will have here F times R times sine theta and then this unit vector. Note that now F and R, they are magnitudes of these two vectors. If I now draw this position vector again, and I shift this F perpendicular vector where its tail connects with the tip of the position vector, and with that I will also shift this F vector back to its original place, then you can clearly see that F perpendicular times R will give you a counterclockwise moment, about 0.0. You are multiplying the component of the force that is perpendicular to the position vector R. And you achieve all that when you cross your R vector with your F vector, R cross F. Note that if you were to do something like this, F cross R, then that would be wrong. So this is the position vector, this is the force vector. If you do F cross R, then instead of F perpendicular in this direction, you would have R perpendicular in this direction. In other words, you would have something like this. This is your force vector, this is R perpendicular. I'm going to shift it here so that its tail would meet with the tip of the F vector. And so this is your entire position vector here. And now, even though I would end up getting the same magnitude, I would have a clockwise moment instead. That's when I write F cross R. But that would be wrong because the force is the one that determines the rotational direction. This is your position vector, this is your force, and so you can physically see that it creates a counterclockwise moment. And that's why the formula for calculating moments is the position vector cross the force vector. That's the standard formula for calculating moments about a point. It has to be R cross F, the position vector cross the force vector. If you do F cross R, then you will get a wrong direction.